matrix of T, what's that equal to? Matrix of T was what? What happens when we multiply these? We get 1, 3, 3, 7, and minus 1, looks like minus 1. Hey, what do you know?
So wait, this basically means the matrix multiplication is the same as function composition.
Right.
That's why it's not, and that's why it's not reversible.
That is a very good viewpoint. So if T and S are composable, in other words, if they have appropriately matching dimensions, right, then the composite of T, I'll write it the other way. I mean, the matrix of T composed with S is, in fact, the matrix of T times the matrix of S, like that. So that's the theorem, is that the matrix of a composite is the product of the matrices composed. Another way to look at this really is that that's why we define matrix multiplication as we do. It's so that this would happen, in fact. It's also why matrix multiplication is associative, because function composition is associative. What came first? What came first in the olden days was solving two systems of equations, one after the other. And when you substitute the variables of the second equation into the first, and then you look at the relation between the coefficient matrices of the original system and the one that's being composed with, you get some new system, kind of like what we did at the start of today. And that new system would have the product of the matrices of the coefficient systems which are composed. I think that's where it originally was seen, but thankfully that's not how we look at it. Yeah.
I'm still kind of confused with the notation of the R3, R2, R. Can you just walk through what's going on here?
Sure. When I take the composite of S and T, right, which one comes first? T. Yeah, because that's when we feed things to compositions, it goes like that. So we get the T. T starts with R3. It outputs an R2, right? And then that's going into the S, but the S goes from R2 to R2. So in total, the whole thing is S composed with T, like that. Uh-huh. No problem. Now, of course, there's natural questions to ask, like, what are the different kinds of linear transformations? What do they do? When do you, when does the line stay? Oh, I thought I had till 4:45, and that was really sad, but I realized I'm okay. So, when does a line stay a line, and so forth and so on. If we look in my, if you look in my notes, which I have posted for you guys, which might be useful, I don't know. I mean, I hope they're useful. I more or less taught this course out of them last time, But we were using lay, and so Dr. Smith is not a fan of that book for various reasons, and that's fine. And I mean, I've been Shore is different for me, and I'm enjoying it. It's got new examples, and okay, so I still haven't said anything about some of the examples in chapter 2, right? Like he's got things on discrete dynamical systems, and like the Markov chain idea. I would encourage you to read those just in case I don't ever get back to them in lecture. It's possible, because I think next time I'm going on to determinants. I'm not sure. It kind of depends on whether or not you guys have homework questions. Oh, don't look at this. This is hideous. Look away. This is homework from the other linear. No. Let's see here. We don't want to look at that, right? Real linear? I wouldn't say that. It's just different. Where was I? Oh, yeah. Wait, no, wait. All right, somewhere in here, there's a file called Math 221. Well, there are many, but we're looking for the one. You see the flaw in my labeling system. That seems like cheating, though. I'm looking for this one. There we go. So in here, I have a chapter on linear transformations and coordinates. Now, we haven't gotten to linear transformations. Excuse me, I haven't gotten to coordinates yet. Give me a few days, we'll get there. But this does have, and this one's a little bit more theoretical than you guys. I mean, you got to skip past some stuff in here for the moment. But there are some nice pictures that we can just look at together for a second here, and I'll put this away. We won't spend too long. I mean, this doesn't really accomplish much, I don't think, except to just give you a sense of like what can happen with a few different examples. And maybe that's worthwhile. One of the reasons I really do like Shore is what he's done is he's woven the notion of a linear transformation throughout the book. So like he keeps coming back to it, you know, and just like, hey, this is what goes on with the linear transformation idea in each chapter. And so this is just our first sort of, what's the word, contact with it. So I'm studying here what happens for this linear transformation if I take the unit square and then I map it. If we multiply the second component by 2, it like stretches it out. So this is one thing a linear transformation can do. It can leave one direction alone, and it can just kind of like the other direction, right? So these kinds of stretchings are possible. That's called the dilation. It can dilate both directions in the same way, like it's taking x and y and both expanding them by a k factor. So it just makes the unit square bigger, like that's possible. It can invert it. So here, minus the identity matrix for the standard matrix just flips the unit matrix like that. If you look at the 1, 2, 3, 4 matrix, it does some kind of funky thing. It takes this guy and it kind of shears it and yeah, like that. But lines map to lines. So like this line segment is that line segment. This line segment maps to that line segment. This line segment maps to the top line segment. That line segment maps to that line segment. So there's some kind of like preservation of the structure of the square from one side to the other. Well, that's a parallelogram over there, right? But you also have these. This is a linear transformation. This is a rotation by 45 degrees. Rotations are special in that they maintain both the angles between vectors and the distance between points. And they also fix the origin. This is a rotation. The inversion also does that, but it's not a rotation. Rotations also maintain, like if in rotation, if you have like this vector, right, and that vector, if I go from the bottom vector to the top vector, that's a counterclockwise rotation, right? If I take this square and I map by a rotation, I'm still going to have the same relation between the legs. Like it's still going to be the case that this leg is a counterclockwise rotation over to that leg in the new space. So like rotations maintain orientation between vectors as well as distance between points and angles between vectors. Rotations are fascinating. This is a rotation and a dilation. So what you're looking at is a rotation by 45 degrees followed by a dilation of root 2. So it takes the unit square, and my picture's not very good, but it's rotating it, and this is actually a bigger unit square because that has length root 2, whereas this is length 1. So my picture's not to scale, so sorry. That's a rotation by an arbitrary angle right there. What is this? Whatever. Oh, that's the identity. Here's a stupid one. Look, the identity transformation. Hooray. I guess I was like, well, while I'm at it, there's no more work. Now, here's the more interesting ones. Rank 1 matrix, you lose dimension. That's the meaning of rank as it relates to linear transformation. If you have less than full rank, when you feed it something 2-dimensional, you might get out something 1-dimensional or less. So here, I feed it this 2-dimensional square. You guys know what that means just from like common English. But we will give a technical meaning to dimension in here by the end of the course. Actually, not too long from now. As you can see, the output, 1-dimensional. We lost something because the matrix just doesn't care about what happens in the x direction, right? It ignores it, essentially. It projects. This is a projection. There's also that projection like this. So this one would be, you know, I've got, I got the matrix up there somewhere. This one also, though, you might think, well, that one's going to be okay, right? There's no zeros in there, but no. That has rank 1. That's going to lose something. Here's what happens. you feed the unit square into that 1, 1, 1, 1 transformation, and it just like that. I forget which line goes to which, but you could sort through it. I think it's in the text there. And so I have I attempted some pictures. Here's a picture of a linear transformation from, let's see here, I'm going from what? From R3? No. From R2 to R3? Yeah. So this is going from XYZ space to XY, well, excuse me, from XY space to XYZ space. And the way I look at it is it takes this unit square and it kind of just pastes it up there. So it maintains the two-dimensionality, but it's not what we'd call an onto mapping. See, the codomain is all of R3, right? And yet we're only covering this one little bit of it. So.
How would that maintain two-dimensionality?
Well, it's a square, it's two-dimensional. Yeah, but it's two-dimensional. You had Calc 3, yes?
Yeah.
So surface integrals is two-dimensional. Surface is two-dimensional, even though it's in three-dimensional space, because it's got two parameters. The number of parameters on the object is the dimension, essentially. And this one, I got a little bit more adventurous. I look at a unit cube in 3 dimensions with this 1, 1, 0, 1, 1, 1 map. So that takes us from 3 dimensions to 2 dimensions. And what it does is it takes the unit cube and it maps it to this parallelogram. I've done some color coding. So like this green gets mapped to that, the blue gets mapped to that, and the vertical legs to the cube get mapped to these guys. So there's all kinds of things that are possible with linear transformations, whether you're going from the same dimension space to same dimensional space or not. Oh, I don't have a picture for this one. This is R4. Oh, here's my picture. So this is the hypercube in R4, and it gets mapped to the line segment in R. Haven't you ever seen a picture of a hypercube? There it is, right there. No? Sorry. Want to see a hypersphere? Check it out. There you go. 3-sphere. Sorry, it was funnier to me. Oh, yeah, I'm plumb out of pictures at this point. Listen, guys, there's something much deeper I wanted to do today, but I spent time on your homework, so we didn't get to it. And that's fine. I'm not complaining, but I want to tell you what I was going to do because it's important. So the other idea, linear transformations in and of themselves are not that interesting, right? I'm sorry. That's just, I should never say such a thing in this course. That's just horrible what I just said. But the thing I'll show you next time is that we could do something much more interesting. You remember in Calculus 1, you could take a curve, right, like this, and you could take this point and replace the curve with what? With its tangent line, right? And so if you're close enough, right, if you're like in here, it's a really good approximation to the function, right? So if I have something like a function of x and y, say it's equal to x squared plus y squared and then xy. And I want to approximate this function. Now, is that a linear function? That is not a linear function. This is not, you cannot write this by matrix multiplication of a vector of unknowns. But there is still a well-defined procedure. I can write this as f of like p plus h comma k is approximately equal to f of p plus the Jacobian matrix of f at the point p times hk. So there's a generalization of the tangent line to functions of several variables where this piece right here is basically a linear transformation. If you want, I could say that the change in f we can approximate by the differential at the point p acting on this h comma k. So this differential is a linear transformation. The linear transformation gives me the best approximation to the change in the function, well, in this case, mapping at the point. And so I can give you linearizations of functions of several variables just using matrix multiplication. Now, I do need to teach you guys how to take partial derivatives, because not all of you have had Calc 3. But trust me, you should welcome that. Like, partial derivatives, not going to be a problem, all right? Like, Dr. Smith is a little bit worried because his second project has, like, partial derivatives, and he's like, they're not going to understand. It's got partial derivatives. I'm like, no. That's not the thing to worry about. Students do not have trouble with partial derivatives. That's not at all what the problem is ever about. So anyway, we'll come back to this, and I'll actually show you this. If I'm lucky and I get Mathematica working, Dr. Smith actually has this beautiful Mathematica notebook where he illustrates the several dimensional Newton's method the book talks about for a specific graph. He actually has like the curved surface and the interpolating plane and like the sample point dancing back and forth as it like zooms into the zero of the it's really cool. But I have like 13 emails with Mathematica to do before I can get Mathematica running. So we'll see if that happens before I see you again. Odds are against it, but we'll try. So anyway, thanks guys. You should ask Dr. Smith to show you that. He's already got Mathematica working on this machine. I'll ask him to show you guys. So Thursday, I'll ask him to show you the Newton's method thing he has.
We have a quiz and class.
Yeah, quiz and class. Most